Welcome back to JVM Internals Crashcasts. I'm your host Sheila, and today we're diving into the fascinating world of Android Runtime, or ART. We're in the final stretch of our alternative JVM implementations chapter, and I'm excited to explore this unique runtime environment with our expert Victor. But before we begin, let's start with a quiz question for our listeners. Victor, would you like to do the honors?
Certainly, Sheila. Here's a question to get our listeners thinking. In terms of app startup time, how much faster is ART compared to its predecessor, Dalvik, on average? Is it A, 10% faster, B, 25% faster, C, 50% faster, or D, 100% faster?
Ooh, that's an intriguing question, Victor. It really makes you wonder about the performance improvements ART brings to the table. I'm sure our listeners are curious to find out. Now, before we dive deeper, could you give us a brief overview of what Android Runtime is?
Absolutely, Sheila. Android Runtime, or ART, is the runtime environment used in Android operating systems since version 5.0, Lollipop. It replaced the previous Dalvik virtual machine and was designed to improve the performance and efficiency of Android applications. Unlike traditional JVMs that we've discussed in previous episodes, ART is specifically tailored for mobile devices and the Android ecosystem.
That's interesting, Victor. So, ART is not exactly a JVM, but it serves a similar purpose for Android. Could you explain how ART differs from a traditional JVM?
Great question, Sheila. While both ART and traditional JVMs execute Java bytecode, there are some key differences. First, ART uses a different bytecode format called DEX, Dalvik Executable, which is optimized for mobile devices. Second, ART employs a combination of ahead-of-time, AOT, and just-in-time, JIT compilation, whereas most JVMs primarily use JIT compilation. Lastly, ART is designed to work within the constraints of mobile devices, such as limited memory and battery life.
That makes sense, Victor. You mentioned AOT compilation, which is something we haven't discussed much in our previous episodes. Could you elaborate on what AOT compilation is and how it benefits Android applications?
Of course, Sheila. Ahead of time, AOT compilation is a process where the bytecode is compiled into native machine code during the installation of an app, rather than at runtime. This approach has several advantages. First, it significantly reduces app startup time, as the code is already compiled and ready to execute. Second, it can lead to better overall performance, as the compiler has more time to optimize the code. However, it does increase installation time and storage space requirements.
That's fascinating. So, if ART uses AOT compilation, does that mean it doesn't use JIT compilation at all?
Actually, Sheila, ART uses a hybrid approach. While it initially relied heavily on AOT compilation, more recent versions of Android have introduced a combination of AOT and JIT compilation. This hybrid approach aims to balance the benefits of both methods. JIT compilation is used for code that's frequently executed, allowing for runtime optimizations, while AOT compilation is still used for critical parts of the application.
I see. That sounds like a clever way to get the best of both worlds. Now, I'm curious about how garbage collection works in ART. Is it similar to what we've discussed in previous episodes about JVM garbage collection?
Great question, Sheila. While ART's garbage collection shares some similarities with JVM GC, it's specifically optimized for mobile devices. ART uses a concurrent copying garbage collector, which means it can perform most of its work without stopping the application threads. This is crucial for maintaining smooth performance on mobile devices. Additionally, ART's GC is designed to be more memory efficient and power conscious compared to traditional JVM garbage collectors.
That's really interesting, Victor. It's clear that a lot of thought has gone into optimizing ART for mobile devices. Could you share an anecdote or interesting fact about ART's development or impact on Android performance?
Certainly, Sheila. Here's an interesting tidbit. When ART was first introduced as an experimental runtime in Android 4.4 KitKat, Some developers reported that their apps ran twice as fast compared to Dalvik. This dramatic improvement was one of the reasons Google decided to make ART the default runtime in Android 5.0 Lollipop. It's a great example of how significant the impact of a runtime environment can be on overall system performance.
Wow, that's impressive. Now, I'm sure ART isn't without its challenges. What are some of the limitations or ongoing areas of improvement for ART?
You're right, Sheila. While ART has brought many improvements, it does face some challenges. One is the increased storage space required for AOT compiled code. Another is the need to balance AOT and JIT compilation to optimize for both performance and battery life. Additionally, ART needs to constantly evolve to support new Java language features and optimize for the latest mobile hardware. Google continues to work on these areas in each Android release.
Thank you, Victor, for that comprehensive explanation. Before we wrap up, let's reveal the answer to our quiz question. What was the correct answer for how much faster ART is compared to Dalvik in terms of app startup time?
The correct answer is B, 25% faster. On average, ART provides about a 25% improvement in app startup time compared to Dalvik. Of course, the actual improvement can vary depending on the specific app and device, but this gives a good general idea of the performance boost ART brings to Android.
That's a significant improvement. To summarize what we've learned today, Android Runtime, ART, is a specialized runtime environment for Android that replaced the Dalvik VM. It uses a combination of AOT and JIT compilation to optimize performance on mobile devices. ART has a concurrent copy and garbage collector and is designed to improve app startup time, overall performance, and battery life. While it faces some challenges, it continues to evolve with each Android release. Next time, we'll be starting our new chapter on JVM in cloud and containerized environments, beginning with JVM in Docker containers. It's sure to be an exciting exploration of how the JVM adapts to modern deployment environments. Thank you all for listening to JVM Internals Crashcasts. If you've enjoyed this episode, please subscribe and leave us a rating. Your support helps us continue to bring you in-depth explorations of JVM internals. Until next time, keep exploring the fascinating world of JVM technology.